So let's say you're interested in teaching a student how to solve Poisson's equation. Now, this is a partial differential equation that shows up quite frequently when modeling physical phenomena such as heat transfer, elasticity, gravitation, and so on. Now, the way students are usually introduced to solving this equation is to learn how to construct analytical solutions, usually on simple geometries and involving sort of simple functional forms for the forcing function and boundary conditions. Such methods can result in reasonably pretty solutions, and they do offer quite a bit of insight. But unfortunately, such analytical methods don't extend easily to more realistic geometries, complex functional forms, or even more complex equations. In practice, though, the way such differential equations are actually solved are through computational methods, such as the finite element method, which are usually introduced later in the student's curriculum. I feel it's a good idea to expose students to numerical tools fairly early on in their study so that they can have a toolbox to play with equations and get a concrete feeling for how these equations behave. I believe that this augments their classical theoretical study quite nicely. In order to do this, I have implemented an online version of the FEniCS project. FEniCS is an open source research project that offers an intuitive Python interface for easily posing and solving differential equations. Now what you see here is FEniCS sitting inside a Python Django application that I'm working on. Let me show you how this works through a simple example. Returning to the Poisson's equation again, we have negative Laplacian of u equal to the source term. We have homogeneous Dirichlet boundary conditions and the normal derivative of the field equals some given value on the Neumann boundaries. So for a specific example, let's consider a square plate with Dirichlet boundary conditions on the left and right surfaces and Neumann boundary conditions where the derivative goes to sine 5x on the top and bottom surfaces and a source term that's some sort of exponential decay from the center. Of course, we can go through standard mathematical arguments and end up with what's called a weak form, which is what's used in the finite element implementation shown on the left. So what you see here is some simple Python code that implements a numerical method for this differential equation for these given conditions. So for example, we have a unit square domain, we have some function spaces for the fields u and v that happen to be continuous Lagrange functions of a certain polynomial degree. We have Dirichlet boundary conditions on the left and right surfaces. We have that the field goes to 0 on the left and right surfaces. We have the functional forms for f and g as defined in this figure. So finally, we pose the weak form of the problem and we actually solve it. So we get the solution to the differential equation. So we have homogeneous Dirichlet boundary conditions on two surfaces, Neumann boundary conditions on the other two surfaces, and some little bump in the middle that comes in from the source term. In this interface, you can actually now start to fiddle around with the differential equation. So suppose the student wonders what would happen if another surface or another edge goes to 0. So let's just set another edge to 0 and try to solve the equation again. They end up with a different result. So they can start to fiddle with, let's say, the functional form for the source term. And we can make it really simple if we want. And we can set the force surface to 0 as well, just for fun. And we solve the equation, and you end up with this really simple solution. So in this manner, students can play around with a toolkit like this and get a better feeling for how the equations behave. And since it's all presented online, there's nothing for the students to install or anything like that. I believe that such interactive technology will play a vital role in online education. And my next steps for this prototype are to extend it to simple mechanics equations and to use this tool to help teach students concepts in mechanics, as well as serve as one way of testing their understanding. Thank you for listening. Please get in touch with me if you're interested in working with me or would like to know more about my efforts.